Finding the probabilities for an x limit using the z distribution. So what we need to understand is that many numeric random variable, for example, if you're looking at electricity consumption, delivery time, or a product mass, they follow a normal probability distribution where they have their own mean and their own standard deviation. Because of that, what we can do is that we use the standard normal z table to find probabilities associated with the outcome of these numeric random variable. But in having said that, each x value from our normal data on top here must be converted into a z value, which is then going to be used to read probability from the appendix table, which we already saw and we know how to use. The formula that we use to perform that conversion is this, where our z will be equal to x minus the mu divided by the standard deviation. So we are converting our x into a scenario where our mu should be equal to 0 and our standard deviation is equal to 1. Only under those two conditions then we can be able to read from that table. So figure 5 here, what is showing us, and this scenario calculated, is just one of those conversion. They are showing us the difference between the area under the normal distribution, where our first x is 14 and our second x is 20, and the mean is also 20 with a standard deviation of 4. So our first x here is 14, our mu is 20, and then also our second x also lies somewhere here where it's 20, and this is the probability that we've read off the table. The way we do that, we said z for x equal 14, we see z was equal to 14 minus 20, and we divided it by the standard deviation, and we got minus 1.5. From this minus 1.5, we went on to our table. Let me just show you. If I open the table here quickly, we don't have a minus, but there's a 1.5, so we look for 1.5 here. You can see here 1.5. For some reason I can't access the alright, so you see here there's a 1.5, and from there we see this value here 0.4, so 0.4332, right? So let's just cut them off, let's make them disappear, and you can see this 0.442 is actually the one that is under this curve right here. Okay, so this is the value under this curve, and that's how we got this z. So we've converted our x14 into this 1.5. Same thing happened for 20, and because we know that we bring them to a condition where mu is equal to 0, it was normal that our mu 20 has become a 0 as well, so which was just a confirmation, and we've worked that out. The meaning of a z value, what it means, it simply tells us that our x is actually minus 1.5 standard deviation below the mean. So these values here are just how many standard deviations are our limit from the mu. So if we had something of 2.5, this would have meant then we have 2.5 standard deviation be above the mean. So these are telling us how many standard deviation away we have from the mean. Now that we've done that, let's just pause, read this question, and try to solve this scenario that is going to look into depth on how we can convert our values. Okay, welcome back. So for A, we need to find the P of the first x's, 45 and 51 here. The step number 1 that we need to do is to sketch this. where we show that our mu is equal to 45, and we are also looking for the limit between 45 and 51. So I'm just going to put it this way, and our x here is equal to 51. We know that the standard deviation here is 8. So we are looking for the probability within this here. And the second step now, which is the easiest one now, because we know the formula for x equal to 45, let's convert this into a z. Then we'll get a z of 45 minus 45 divided by 8, which is equal to 0. And for an x equal to 51, our z will be 51 minus 45 divided by 8. Then we get 0.75. Rewriting now, thus we have now a p of 0 less than z less than 0.75. So this has become 0 and this has become 0.75. Now we'll just go to our table. Going to the table now, what we are going to do is find where the 0.7 and 0.05. We'll see that under there we have 0.2734. Therefore now we know that this is equal to the probability of 0.2734, and that's what we have here, 0.2734. In other words, now we can say that we have 27.34% chance of randomly selecting there, because this is the probability that we have under those conditions. Now let's look at the second scenario. The second scenario, we are looking for a p of x less than 48, because what is the chance of randomly selecting or the parcel that will take less than 48 minutes to deliver? We'll first start with our curve. Let's sketch our curve here. If we know that our mu or population mean is 45, what we are looking for is anything less than 48. So 45, we all agree that 48 should be somewhere here. This is not a 9, it's a 4. Therefore, anything less than 48 then will mean it's whatever is found in this area of the curve. All right, but we also know that from this side here, this probability is already known. It's 0.05. What we'll be actually looking for is the probability just between here 0 up to this z. Then we'll add that to the 0.5. Here is how you can write it. You would say that you need to split that. You work out first when x is equal to 48. Let's first find that z. Your z will be 48 minus 45 divided by 8. You get 0.375, which I'm going to round off 0.38 here. And after doing that, like I said, now we are splitting the two. So first there's a p of z less than 0, which we already know, the entire thing here, and the probability of 0 less than z less than 0 0.375 rounded off here, which is there. Now what I'm going to do is when I go on the table, okay, so 0.38, then I'm gonna first find 0.3, and 0.008 is right on top here. Then I'm gonna get 0.148. So this is equal to 0.1480. This is now how I'm going to write. So I'm gonna add this to this one. Then my p of x less than 48 is equal to p, like I said, z less than 0.375, which is 0.5, because we know the first half. We'll add this 0.148, then I'll get 0.6480, which is now 64.8%. So we have 68.4% chance of randomly selecting a parcel that will take less than 48 minutes to deliver.